Welcome students. Now we will discuss about antenna apertures. So today topic is antenna apertures. So this topic is about the area over which the antenna can extract the power. So how much power can be extracted from area, right? So this is the estimation of the area, right? It is not the estimation of the power. So power reception from the area, that is called as apertures. So whereas this antenna aperture is depending upon the size of the antenna. For the case if it is a linear antennas or wire antennas, the size of the antenna is very smaller. So power capturing will be proportional to this antenna apertures. That is very important factors. So if we take large dimension antennas whose aperture dimension is very bigger, so we can extract the maximum power. So usually, since we are going to extract power from the area, then the unit for antenna aperture will be calculated in terms of meter squared, right? So again I will tell that antenna aperture is nothing but the power received from the area. So from how much area the power can be received, that is called as antenna aperture. See here we have dipole antenna and loop antennas, slot antennas, patch, reflectors, horn and helical. And for these antennas are having different in dimensions. So because of these dimensions, the aperture will be varied. So the power reception also will be changed. So power reception is proportional to one of the factor is dimension of the antennas. What are the types of apertures? The one is physical apertures, and second one is effective apertures, scattering apertures, loss apertures, collecting apertures, right? So whereas physical aperture says about the physical dimension of the antennas, effective aperture says about what is the aperture over the physical length or physical dimensions. Scattering aperture is nothing but and power, this is the calculation of power scattered on the wall of the aperture antennas. Loss aperture is also, that is calculating the loss factors. Collecting aperture is we are going to combine the entire apertures due to loss, scattering, effective, physical, all those things, right? So antenna aperture is the measurement of area, that is from how much area the power can be received from by the antenna systems. So physical aperture says about the physical dimensions. See here we are taking the horn antennas. So in the horn antenna, the aperture size is rectangular in shape. See here, this is a rectangular shape. A is the length of the horn and B is the breadth of the horn. So where aperture calculation by taking the area calculation of the horn antenna by multiplying A into B. So unit is in meter squared. So the area of opening is called the physical aperture for any antenna systems. And the power density can be calculated by taking this the received power can be calculated by taking this power density W into the physical aperture of the antenna. So received power depends what is the power density multiplied with what is the aperture of the antenna systems, right? So effective aperture. So what do you mean by effective aperture for this antenna systems? The effective area simply represents how much power is captured from the plane wave and delivered by the antenna. So that is the effective aperture. When we receive power, it is less than we calculate due to the following reasons. So received power will be affected by the following cases. For example, in the horn antennas, horn is not uniform over openings. That is one of the factors. And E field must be 0 at wall, but not practically. So that is, we can say that it's due to ohmic losses, and there is a tapering loss and there is a conducting losses. And because of these loss factors, the received power may be some deviations from the exacted calculated values, right? And this is the general formula for the relation between effective aperture to the gain of the antenna. So AE is equal to lambda squared by 4 pi times the gain of any antenna. So by taking this lambda is equal to C by F, then we can modify the effective aperture equations to C squared by F squared into G by 4 pi, right? So antenna aperture can be calculated with by taking the actual antenna impedance values along with voltage and what is the power density of transmitting, all those things we can calculate. So first equation says about effective aperture the formula is equal to, this is the voltage squared by 2 times of what is the power density, multiply with RT by RR plus RL plus RT whole squared plus the reactance of the antenna and transmitter part whole squared, right? Now we are going to calculate what is the maximum effective aperture. From this effective aperture, if you are going to match the conjugate values, because we know that for maximum power transfer we are going to match XA is equal to minus XL and this value is equal to R, then we will get all these terms. This reactance part will be getting cancelled and we are getting the maximum values. So this is called as maximum effective aperture. Next equation, this is called as scattering aperture equations, that is modulus of Vt squared by 8 times Wi, the power density, multiply with Rr by Rr plus RL whole squared. So for this scattering aperture we are going to calculate radiation resistance of the antenna. For loss aperture we are going to calculate what is the loss factor. So what is the loss resistance of the antenna. So loss resistance due to dissipation of heat energy. The power is dissipated as the form of heat. Okay. So while transmitting power, in any cases there is a chance of dissipating heat. So that also we are going to consider for calculating the receiving power. So now the collective aperture or capture area is by calculating the effective area or effective aperture plus scattering aperture plus loss aperture. By combining all the three equations we are getting the collective aperture, and this is the aperture efficiency. So aperture efficiency is nothing but for the entire physical area what is the maximum effective area or what is the maximum effective aperture. So this is the ratio for getting the aperture efficiency. For entire physical area of an antenna systems, how much power can be received from the area, right? This is the maximum effective area to this physical area is the calculation for aperture efficiency. And this is the relation between maximum effective aperture to the directivity of antenna. So maximum effective aperture is proportional to the directivity of the antenna, where directivity and gain are equal when there is a 100% efficiency, right? So the G will be replaced by this G naught, and this already we discussed about aperture efficiency. It is a ratio of maximum effective area to this physical area. Now we are going to discuss about what is the relation between directivity and maximum effective area. So we have to start from this cases. Here we have an antenna 1, here we have antenna 2, that is the transmitter part and receiver part. The distance is R, and the directivity of this antenna is dt. Directivity of receiver is dr, and aperture of the transmitter is at, whereas aperture of the receiver is ar. So all these terms are given over here, right? So W naught is the power density of isotropic radiator or isotropic antenna, whereas Wt is the radiation density of that is the power density of the transmitting antenna, where Wr is the power density of the receiving antenna. So from this we have to start. Suppose if the antenna 1 has an isotropic radiator, that is it radiates power in all the 360 degree, then the power density can be calculated by taking this, what is the power transmitted by 4 pi r squared. Then actual power density of the transmitter can be taken by taking this radiation density of isotropic sources multiplied with directivity of the transmitter. Then we can use this formula over here. Then we are getting what is the power density of the transmitter part. So this is the relation. Similarly for receiver, so received power can be calculated by taking what is the power density and multiply with what is the aperture of the receiver. So we are going to combine these relations. So from this we can take what is dt into AR. Similarly, what is dr into AR? If you are going to interchange your antenna number 2 as a transmitter, antenna number 1 as a receiver. So if we interchange from here, if we are going to use this receiver as a transmitter and this transmitter as a receiver, then we can write this equation. The above equation can be written as this. So here dt AR is equal to PR by PT of 4 pi r squared. Here dr AT is equal to PR by PT of 4 pi r squared. Now we are going to combine these two equations. We are getting the relations. So this is the relation of your transmitter part, this is the relation of the receiver part. So by combining these two we are getting this relations. dt by AT is equal to dr by AR, and suppose if we increase the directivity of antenna, increases its effective area in directly proportional. So DOT is nothing but maximum directivity of the transmitter. It is the maximum directivity of the receiver. By taking the ratio, if the aperture is maximum in the transmitter, if the aperture is maximum in the receiver, this is the relations, right? If the antenna one is isotropic, then the directivity of the isotropic transmitter is 1. So this DOT value will become 1. So we can write what is the value of ARM as well as ATM. So ATM is nothing but maximum aperture of the transmitter is equal to maximum aperture of the receiver by the maximum directivity of the receiving antenna. So this is the basic relation between your aperture of transmitter, aperture of the receiver to this directivity of the receiving antenna. Now by calculating, for example, if we take the Hertzian dipole whose length is very much smaller, so L is very much smaller than lambda, that is a short dipole whose effective area is 0.119 lambda squared and the directivity is 1.5. If you put all these values together over here, so this is the maximum directivity 1.5, substitute over here, and the effective area is 0.119 lambda squared over here. Then we have the transmitter maximum aperture of the transmitter lambda squared by 4 pi, and the above equation can be written as these terms. So DOR of lambda squared by 4 pi, and now this is the maximum effective aperture equation. So the maximum effective aperture is equal to lambda squared by 4 pi into D naught. So this is the relation between what is the directivity and what is the maximum effective aperture of the antenna systems. So this is the maximum directivity occurs when it achieves 100% efficient, because we know that gain is equal to gain factor, that is eta times the directivity, right? Suppose if the antenna can able to transmit 100% efficient, then this D naught can be replaced by G. So this formula can be written as lambda squared by 4 pi into G also when the efficiency is 100%, right? So this is the required relation for antenna aperture as well as the directivity and also the gain.